Hello, welcome to Unit 9 in Algebra 2. This unit we're going to study the radical function and radical equations. When I say radical, I mean anything that has either a square root or a cube root or even a fourth root or above. We're going to start with this lesson by looking at how the square root and cube root functions can be derived as inverses to the x squared function and the x cubed function that we're already familiar with. Now, in order to find these inverses, we're going to have to use some solving techniques that might be a little unfamiliar. And so we'll be kind of learning two things at once here as we do this. Don't worry, just go with it for now and use your resources and your knowledge to get through it. And it'll start to all make sense as it comes together by the end of the unit. So let's start with example 1.1. We're going to represent the function f of x equals x squared with a table of values and a graph. So we've done this a lot, so I'm simply going to be plugging these in for x and squaring them. I get 9, 4, 1, 0, 1, 4, 9. And then we can plot them on our graph here. This generates the familiar parabola that we're all so experienced with. Now, this curve here is called the quadratic parent function because we can derive all other quadratic functions by using our basic transformations of it. So my question for you is, does this function have an inverse? Now, I know it's been a while since we talked about that, but remember that an inverse function can only exist if the original function passes what we call the horizontal line test. We know that a relation that fails the vertical line test is not a function. But since we'll be inverting it, we need to check if the original function passes the horizontal line test. Well, simply passing a horizontal line over this would clearly indicate that it touches it more than one place. So this does not pass the horizontal line test. So that's exactly what we're going to say. That f does, I'm going to say f has, but I should say f does not. F does not have an inverse function, I should say, because f fails the horizontal line test. Or we might be more precise and say that it is not a one-to-one function. Our next question is, what domain restrictions could be put on f of x equals x squared to allow it to have an inverse function? So if I were to go in here and just remove all of this part here, then it would pass a horizontal line test. And it's not the only way we could restrict the domain, but if we restrict the domain to x greater than or equal to 0, by explicitly limiting the domain, then it would have an inverse function. So that's what we're going to do. We're going to find the inverse function of f of x equals x squared with the domain limited to x greater than or equal to 0. To find an inverse, the first step is, if they have f of x, rewrite it with y. Then, here's the inverting. This is us doing the inverse step right here. It's very simple. You simply switch the x and the y values. Now we're going to solve for y. When we have y squared, we have learned that we can use the square root. If all we have is a squared term, we can use square root, but we need to use plus or minus. But in order for this to be a function, we can't have both a plus and a minus, because then we're getting two values for y for any one x value. So we need to make a decision. We need to pick either the plus or the minus. And what tells me is this here. Because I need to have my range match of my inverse match the domain of my original function. Recall that an inverse maps the range of f back to its domain. And since my domain was x is greater than or equal to 0, I need my range to be so. The square root function can never result in a negative value. So I must pick the positive to get all the positive values. So we're going to say f inverse of x is equal to the square root of x. And what I was saying before is that the square root function will never evaluate to a negative number. So by simply choosing the positive one, we ensure that the range is only greater than or equal to 0. Let's plug in some numbers and make a table of values. We could simply borrow these values here as long as they're the positive ones. Remember that the square root of a negative number is not a real number, and we are only graphing in the domain of real numbers. So I'm going to start with x equals 0, and the square root of 0 is 0. I'll go to x equals 1, who has a square root of 1. And then the next number I'm going to go up to is 4, because that's the next number that has a next integer, I should say, with a rational square root, 2. The square root of 9 is 3. The square root of 16 is 4. 25 is 5. 36 is 6. And we want to be familiar with those numbers, particularly these here, because we'll see them a lot. Let's go ahead and plot these. 0, 0, 1, 1, 4, 2, 9, 3. This is f inverse of x equal to the square root of x. That's the square root of x function that we're learning. The original function, when graphed only for a positive domain, looks like this. And that was f of x equals x squared. You can see that they are, in fact, reflections across the diagonal line y equals x. Can you see the reflection? That's one way they're related. They're also related in that for every point on f of x, say 2, 4, the point with opposite x and y values is on the inverse, 4, 2. The domain of f inverse is x greater than or equal to 0, or 0 to infinity. And the range is also 0 to infinity. All right, one function down, we need another one. Now we're going to look at x cubed. We briefly looked at this at the end of the last unit. Negative 3 cubed is actually a negative 27. Negative 2 cubed is a negative 8. Negative 1 cubed is negative 1. 0, 1, 8, and 27. So I'll just plot a few of these values here. And we get this shape. This is the x cubed shape. We might say that this is the parent function for the function x cubed, but that's actually not quite true, because if you're allowed to have x cubed and x squared, you can actually get some shapes that you can't make with transforming that. So I'll call this the parent function for the x cubed only family. So as long as we have just x cubed, not any x squareds or things like that, then we can say this is the parent. All right, does this function have an inverse? Well, this one does, because the cubing results in a negative number even when the x is negative. It still passes the horizontal line test. There's no place where the curve would touch a horizontal line more than once, so it must have an inverse. It passes the horizontal line test. Therefore, we should be able to find it. Oops, I copied this over twice. And we don't need a domain restriction in order to find this. Let's go ahead and do that. Simply start with the equation y equals x cubed, and we'll flip-flop these values, x equals y cubed. And then this time, instead of the square root of both sides, this is new for us, I'm going to take the cube root of both sides. But I do not need a plus or minus on the cube root, because the cube root of a negative number is negative. The cube root of a positive number is positive. It is 1 to 1. We do not need to fix it with a plus or minus. Okay, let's plot both of these functions. Our original function, just to replot it again so we can look at it, was like this. 0, 1 cubed is 1, 2 cubed is 8, negative 1 cubed is negative 1, negative 2 cubed is negative 8. And you want to be able to generate that list of numbers pretty quickly, okay? Now we're going to plot the inverse in orange. All that's going to happen is the xy values will flip. So 2, 8 becomes 8, 2. This point here, that 2, 8 is now at 8, 2. And the graph kind of bows the other way. And there we have it. The domain for both of these functions is negative infinity to infinity, and the range for both of them is negative infinity to infinity. How are they related? As we said before, they are reflections across the diagonal line y equals x. For every point on f, if you switch the coordinates, you'll find that point on f inverse. And we might even go further to say the domain of the inverse is the range of the original, and vice versa. All right, let's take a look at this practice problem. I'd like you to pause the video and please give it a try. Okay, don't worry if you got stuck on this one. It's a little challenging. I threw this -6 in here. So let's give it a try. We're going to find the inverse for this specific domain. So I have y is equal to x squared minus 6. I'm going to switch the x and y, and I get x equals y squared minus 6. And now what I need to do, though, is I need to solve this, and I'm going to use square roots. I'm solving for y, and all I have is a y squared, so square roots is a fine strategy. Take the plus or minus square root of each side. Because we're taking a square root, I need plus or minus. And I get plus or minus the square root of x plus 6. But we need to make a decision. Which one of those branches should we take, the plus or the minus? Well, again, we're looking at a domain of positive numbers, so we need a positive range. So we'll take the positive square root. Let's graph both. So x squared minus 6 for x greater than or equal to 0 starts at negative 6. Then 1, negative 5. And 2 squared is 4, minus 6 is negative 2. 3 squared would be 9, minus 6 is 3. So we get this kind of shape here. Now, let's graph the inverse. The inverse is going to have all these points flipped. And we're going to talk more about how to graph this in the next lesson. But we can just use these points and change their x, y values. So 0, negative 6 is now negative 6, 0. It has to be because they're inverses. 1, negative 5 is negative 5, 1. 2, negative 2 is negative 2, 2. And 3, 3 remains 3, 3. We can see that the domain of f inverse is negative 6 to infinity. And the domain of f is 0 to infinity, because it was expressly limited that way. The range of f inverse, notice, is the y-coordinates goes from 0 to infinity, but the range of f is negative 6 to infinity. So you can see the domain of f inverse is actually the range of f, and the range of f is the domain of f inverse. All right, let's try another one. We're going to find the inverse. We'll sketch and find the domain and range of both. This one's another practice problem, so give it a try, and then when you're ready, unpause the video, and we'll go over it. All right. So g of x is a relationship between y and x plus 3 cubed. We're going to switch the x and y values and solve for y. At this point, I need to use the cubed root of both sides. So I'll take the cubed root of x is equal to y plus 3. Then subtract 3 from each side. So the algebra here is not too bad. It's just that we're using g this time, not f. That g inverse of x is equal to the cubed root of x minus 3. First, I'm going to plot x plus 3 cubed. We haven't done a lot with graphing this. We'll focus on that in the next lesson, but it actually is good. If you plug in negative 3, you get 0. Negative 2, you'll get 1. Negative 1, you'll get 8. So it looks something like this. And then our negative side comes the other way. Now, when I graph the inverse of it, negative 3, 0 becomes 0, negative 3. Negative 2, 1 becomes 1, negative 2. And so we're going to have a graph go like that. And this point here, negative 4, negative 1, is now negative 1, negative 4, and the graph goes like this. All right. Try finding the inverse of this, and then graph both with a graphing utility. Okay, hopefully you've paused the video by now and given this a try. We're going to flip the x and y values. Pay attention to that. That's important. Okay, I am going to divide by a negative. So I get negative x is equal to y minus 2 squared. I'll then take the square root of both sides, but I have to use plus or minus. Now, don't think you can't take the square root of negative x. I know we can't take the square root of negative numbers, or we can, at least they're imaginary, but we're only doing with real. This is merely saying that our graph is going to have a domain that requires x to be negative. Because if you plug in a negative number for x, and then there's a negative and times that, it becomes a positive number, which we can square root. Lastly, I'm going to add the 2 over, so I have 2 plus or minus the square root of negative x, but I need to make a decision. The domain was all numbers bigger than 2, so the range of my inverse needs to be all numbers bigger than 2. So we'll once again be choosing the plus, but it could have just as easily been the minus. So f inverse, or y inverse, I guess, of x is equal to 2 plus the square root of negative x. And we'll graph that right quick with the graphing utility. Let's see what we get. So I'll just go to Desmos.com again. And our first function was y is equal to, let me look it up right quick actually. Negative x minus 2 squared. And our inverse, we said, was 2 plus the square root of negative x. Now you can see that these appear to be inverses, but because I didn't limit the domain of the red function, it doesn't look quite right, does it? Well, we can limit the domain by saying something like this: x greater than or equal to 2. And then we've limited the domain. And that gives us a little bit better picture of what's going on. And you can see the symmetry across the line, y equals x, I hope. All right. Let's do the next one. This one's an example, so here I go. Find the inverse of y equals x minus 3 minus 1. Use any domain restrictions that are necessary on the result. So we'll take a look at that. Okay, so first thing I'm going to do is switch the x and y values, and then I'll solve for y, because that's how we find the inverse. Add 1 to both sides, I get x plus 1 equals the square root of y minus 3. And this is kind of new for us, but we're going to undo the square root by squaring. And so that cancels that out, and I get y minus 3 is equal to x plus 1 squared, which gives me x plus 1 squared plus 3 is equal to y. So we can say that that's our inverse, but we'd actually be incorrect. And let's discuss why. The graph of the square root of x minus 3 minus 1 will look something like this. If you plug in 3 for x, that's the smallest x value you can have, you get 0 minus 1 is negative 1. 4 gives you 0. Then the next value you can do is 7. 7 minus 3 is 4. The square root of 4 is 2. Minus 1 is 1. So we get this shape like this. And as you can see, the range, since this can never be negative, the square root is always evaluates to a positive or 0. The lowest value y can be is negative 1. So we have a range of f of negative 1 to infinity. I need to make sure that I have a domain of that over here, because that's the rule. So y is equal to, I said f, but it's y, x plus 1 squared plus 3, and I need to limit the domain to x greater than or equal to negative 1. Once I limit that, then I get this parabola with a vertex at negative 1, 3, but I only have the right-hand side of it. And that gives us the image that we're looking for. All right, so try that same process. Okay, let's see how you did. You should have switched the x and y. And if I do that, I get this shape here. Now, I'm going to go ahead and divide by negative 1, but it turns out it's actually not necessary. Because when I square both sides, I could factor out this negative 1 and square it and make it a positive 1. So we end up with negative x plus 4 squared minus 1 equals y. But we need to restrict this domain. This domain is all real numbers. We need to restrict it so that the domain is limited to the range of this function. Let's graph this function. Let's plot some points. If I plug in -1, that's the smallest x value you can plug in and still get a real answer. -1 plus 1 is 0. The square root of 0 is 0. And 0 plus 4 is 4. Then I have, if I plug in 0, I get square root of 1 is 1. -1 plus 4 is 3. The next number I can do is 3. X equals 3. 3 plus 1 is 4. Square root of 4 is 2. -2 plus 4 is 2. Excuse me. And so we end up, we're starting to see this kind of shape develop here. So you can see because of this negative here, the largest value is 4, and then it goes down. So I have a range that is negative infinity up to 4. So I need to, or in other words, the y values are less than or equal to 4. I need to make my x values less than or equal to 4. And then if we graph this function, we'll end up getting something like this. Okay. Let's do another example. This time we're going to find the inverse of this function. So this is y is equal to x plus 2 squared minus 1. I will flip the x and y and solve for y. Take the square root of each side, plus or minus over here. And then I get plus or minus the square root of x plus 1 is equal to y plus 2. Moving the 2 over, it gives me -2 plus or minus the square root of x plus 1 is equal to y. But since our domain has been limited to x less than or equal to 2, my range should be limited to y less than or equal to -2. So I need to choose the negative branch so that I'm going down. All right, let's take a look at some more practice problems here. I'd like you to find the inverse of each function. Okay, on this one here, you should have flipped the x and y values. So this becomes x equals 4 times y plus 2 cubed, which gives you x over 4 equals y plus 2 cubed. Then take the cube root of each side. And you can just leave it like this. And then move the 2 over. So the cube root of x plus 4 minus 2 is equal to g inverse. And since it's a cube root, we don't have to worry about any kind of domain restrictions. On this one here, this is kind of a review. You just switch the x and y's and solve for y to find the inverse. And there we have it. All right. Lastly, let's review finding the domain of a function. We're having a little bit better understanding of how these graphs look, so this would be a good use of our time. Remember that the domain is all the real numbers that result in a real number output for the function. In order for this function here, in order for the y value to be real, the part under the radical must be 0 or greater. So for my domain, I'm going to solve for all the x values that make that happen. And I get -2x is greater than or equal to -9. So 1x is, when I divide by 2, -2, I flip the sign, less than or equal to 9/2. So that's the domain, -infinity to 9/2. On this question here, we need to be a little more careful. We know that in order for f to be a real number, I need to make sure that this graph is above the x-axis. So we need to make sure that this portion here is greater than or equal to 0. So I will solve that equation. And what I would do is factor this, make it 5 minus x and 5 plus x greater than or equal to 0. And when we have this situation, we should draw a number line. And let's see here, -5 and 5 are the solutions that make this 0. And let's just kind of test some regions as one way to do this. We know that this is when the part on the radical is 0, which should be included in our domain. We can use the fact that we know that 25 minus x squared is a... So since this is a parabola that is opening downwards, this would be, we know that it would go something like this. So I know this is negative, positive, and negative. That's one way we could do that. We could also just plug in these numbers that are separated in these regions. Like, for example, plug in the x value 0. 25 minus 0 is clearly a positive number. And if I plug in negative 6, I get 25 minus 36 is a negative number. If I plug in something like positive 6, I also get a negative number. So you can see our region has been, this is negative 5 and 5 was where 25 minus x squared is 0, but then we've also labeled where the regions are negative or positive. And since we're looking for when 25 minus x squared is positive, this is the interval where this 25 minus x squared is positive, which means that f is defined there. So our domain is this bounded negative 5 to 5. Now, on this last question here, the cube root of x minus 4 is really just all real numbers, because we can cube root anything. So all real numbers are negative infinity to infinity. All right, that's it for lesson 1. I'll see you in the next one.